I share Emacs with you, you can read when I'm doing share screen. All right, so can you see that? Whoops, let's make it full size. Yeah? Are you seeing my Emacs?
No, we're seeing your, oh yeah, I think we can see.
Okay, tell. Okay. So we're going to talk about something called the Curry-Howard isomorphism. And the basic, Curry noticed this first. So Haskell Curry was a logician, and around Church's time, and now I'm in my office, I probably have, oh, maybe I took Curry's book home. Yeah, that makes sense. So I don't have Curry's book here, but, well, who cares? It's a book. You've seen books before, yellow books. So anyway, Curry was kind of neck and neck with Church doing, while Church was doing the lambda calculus, Curry was building on something that was often actually misattributed to Curry, but it's really the Curry-Schoenfinkel system of combinators. So now I do actually have, did I take that home? I might have taken that one home because I thought it's so valuable. I used to like go to used bookstores when I lived. Well, I go to a used bookstore whenever I possibly can, let's say. But when I was much younger, I would go to used bookstores, and there's a lot of them in upstate New York. And I once found this manuscript, kind of like bound in leather, by Schoenfinkel in German. And I didn't really know who Schoenfinkel was, and I don't really read German, just the littlest bit, like what you could learn in high school. But I realized this is a logic book, and so I bought it for like, I don't know, $10. And I think it must be an extraordinarily rare book. I haven't really tried looking up. But anyway, Schoenfinkel invented a very similar system to what Curry had built. And we haven't really talked about the S, K, and I combinators, but you can find them. Oh God, can I remember? I always get confused on this one. It's something like X, Y. Well, and you don't need parens there. Applied to XC. Can somebody look up, or I'll look it up. Can somebody Google S combinator to make sure I wrote it down right? I mean, we can figure it out. So I think that's it. Did anyone find it?
Looks like it's supposed to be XZYZ.
So here's a book by Frederick Fritz. Actually, Mimram talks about it also, but
I think the S combinator is supposed to be XZYZ.
okay, good. Yes, that's right. Okay, so we could look at this in just a minute and figure out the types. But it turns out that actually you don't even need this one. You don't even need the identity. This is insanely a Turing-complete system of computation. Now you could define these things by saying S is equal to lambda x dot lambda y dot lambda z dot x z y z. And K can also be defined as a lambda term, as lambda x y dot lambda y dot x. And I can be defined as a lambda term as just lambda x dot x. So it turns out that these three connectives are complete. And Turing complete. You can write down any computation you want using these. So I don't know. I use it every now and then. I have taught like over the years a little bit about it, but I always forget. Like what does SKK do? And let's give it like a Y. So we look up there and we say, okay, take the K and apply that to Y, and then take the K and apply that to Y. And so, but K applied to Y, so that's my Y, the lambda x. So the first argument, it just returns Y. So actually, there, I wrote the identity function. So I is equal to SKK. So you don't need Y, because no matter what I give SKK, I get the same thing as just using I. So the way that you get to this point, though, is, or the way that you can see this is, what if we try to write down the types of S and K and I? Oh, by the way, a combinator is just, in terms of the lambda calculus, is just a closed lambda term. There's no free variables. So what are the types? Well, I mean, K, all right, K is pretty easy. K is an A arrow B arrow A. And of course, arrow associates to the right. And I is an A arrow A. And so what is S? I mean, I don't know. This is one that I sometimes use in 3015, right? So X must be a function from an A to a B to a C. Somebody, if I'm doing this wrong, help me. And then the Y must be a, the Z is a B, so Y is a B arrow C. Is that correct? And
Isn't
the
Z
Z,
gen A?
I'm sorry, what?
Isn't Z type A, since it's the first argument of X?
Ah, yes, okay. So maybe this is an A then. And then what's the last thing? Z better be a B, and it returns an A. Well, we could run it through your type checker. I could show you this by saying, I don't know, what is going on here? Okay, I don't know, I must have mistyped something. Can't use uppercase names for things, okay. And what is the type of S? T1, T2, T3, T1, T2, T1, T3. Okay, so I did get this wrong. But I think Keegan was like too polite to fix me. This is a C. And this is a T1, an A arrow, B, and this is an A arrow, C. Now, where do you, how do you possibly come through it like this as being complete, a complete system? Well, it turns out that Curry was looking at Hilbert proof systems for logic. And we're going to talk about Hilbert proof systems, natural deduction systems, and sequence systems for building proofs in logic. And the Hilbert systems are extremely difficult to use because you have to build your proof from the bottom. You have to read kind of like from the axioms, from instances of the axioms to the conclusion that you want. But if you look at this formula here and you think of this arrow as implication, these three, I think, are a complete system for a complete Hilbert system for intuitionistic logic. Oh God, now what the heck is intuitionistic logic? So let me just say that, the types of these three are okay, so what is intuitionistic logic? The types of these three combinators and I should probably say here, you know, when arrow is translated to double arrow, which is implies, so we take the arrow, this arrow, which is the function type, and translate it into implication, then we get a complete axiom system for intuitionistic logic. Now, a complete, I should say here, Hilbert-style axiom system for intuitionistic logic. Now, I seriously hope I'm not lying to you. But this Curry-Howard thing works every which way. So let's look at, you know, I don't know. I could either try and open a copy of Mendelssohn, which has Hilbert-style axiom systems, and try to make sure I'm not completely off here. Propositional. The Hilbert axiom system for propositional logic. I just want to make sure that this is come on, where is the axiom system? Right, A implies B implies A implies B implies C implies A implies B implies A implies C. And this one, oh, for classical. So this is for intuitionistic version, I think. And then you add one more for classical, which is not B arrow, not A arrow, not B arrow, A arrow, B. So I haven't explained, you know, so this is for classical logic. So I haven't explained how these axioms are used to prove things. And it's really painful. And I don't even want to go through it really, but you can read about it in Mimram. He talks a little bit about Hilbert systems. So, you know, you can prove stuff. Does anyone want to see a proof?
Sure.
Okay, I need to turn this up. I heard somebody said sure, I think. Okay, so here's a proof that and this one already starts with, so like this is a proof of a form like but we should be able to I didn't really mean to go down this path this far, but okay. All right, well, here's a good one. Here's a good one to show you kind of like just how crazy this is. Let's prove A implies A. Well, there's an instance of axiom schema. So if I label these things by their, so let me just copy this and then put it down here and give them their names as axiom schemas. This is A1, according to Mendelssohn, which is kind of like the, one of the more classic presentations of this. A2 is, I'm sorry, A1, this is A1. This is A2. You don't need I because we can derive it. In fact, that's what we're going to do currently. And then A3 is this one. So this is for classical logic, one is missing. So these, and maybe I should change the A's to be uppercases and so that I'm consistent with my notation here. I apologize. Here we go. All right. I think I got it right here. The types of these combinators, when the function symbol is translated to the arrow and symbol, the implication symbol of logic is a complete, I'll say, form a complete Hilbert-style axiom system for intuitionistic logic. Now, for classical logic, one is missing, and, and I is redundant. Now, up here, we looked at SKK. So essentially what we kind of want to do, and that turns out to be the identity function. And so what we'd kind of like is we're going to try and prove it using these axioms here, that A implies A. So the first part of the proof says, so we're going to try and prove A implies A in this Hilbert axiom system. And so the first thing is to take an instance of A2 So line 1 says, take an instance of A2, but change everything to A. And then the second line says, okay, now you might be able to guess what's going to go on here. Like we can take A1 with wait, sorry. So we can take, this is crazy. So take an instance. So this is an instance of A1. When I learned logic, this is what I learned. The first time around, I hated this. Now take an instance of A2, and the instance of A2 that you're going to take is A implies A implies A implies A. So we're replacing B by A implies A. And of course, these have to go to the right. So that's an instance of A2. And now the third line of the proof says, now from did something wrong above.
Are your instances the wrong way around? So the first one is an instance of A2.
Yeah. I just copied the rule without making it the proper instance. Arrow A. So it's left paren. A implies left paren. Left paren. A implies A. Right paren implies A. Left paren implies A implies, and this should be an A implies A. Double print arrow A implies A. And so now you can see, hopefully, this is an instance of that, because the only rule of proof you have here is modus ponens. And so modus ponens says, look, if you know that P implies Q, and you know that then Q. Now, this should look familiar to you, because this looks a little bit like the function application rule, the typing rule for function application. If I have a function that goes from P to Q, and I have a P, then I can get a Q. And so here, this matches this. So that matches that. And so now that means I have, this is my P. P implies something. I guess I'm missing a paren on the end here to match that one. So I have this and that. So then I get this. I mean, in some way, if you're feeling like, oh God, you know, this is horrible. We're going the wrong way. Caldwell didn't even want to talk about this. I think this is actually incredibly instructive. So this is modus ponens with 1 and 2. And now I can do axiom scheme A1 again with A implies A. And then by modus ponens with 3 and 4, I get A implies A, which is what I was trying to prove. Now, probably, so this is, the rule here is this is an instance of modus ponens with 3 and 4. Now, if I change all these to like imply symbols, then you kind of get the right thing. So here's a proof that A implies A by building up from the axioms. Now, these things are really hard to work with, these Hilbert-style systems, proof systems. Finding proofs can be really difficult. Like, it doesn't follow typically the way that we kind of like conceive of approaching a mathematical problem. And so then in I don't know, 1936 or so. Let me look. I got the paper.
Also, 2 lines up instead of and, you wanted and.
I'm sorry, what?
2 lines up instead of and P, then
Yeah.
you wanted an and P, don't you?
Yes.
Yeah.
And so this is a book that's impossible to find. It took me years to find this copy. I had that library copy checked out for years until I found this, but there's a paper in this. So this book is, I don't know what you can see and what you can't see. It seems to me like my camera is terrible on here, or at least my vision of myself is very jerky. So this is the collected papers of Gerhard Gentzen and investigations into logical deduction. And this really changed, let's see, what page does it start on? 68. This changed kind of like the future of logic in a big way. And really, it doesn't say right on that page what year it's from. I have to look at the introduction. Oh, all right. Gentzen, in this one paper, proposed 4 systems, and I'll have to look up the year in a bit, but in 1936 or thereabouts, I don't know, maybe it was 39. Gerhard Gensen, there's N, K, N, J. Is that, what are they called? What does he call them? You know, at one time, I don't know, like a year and a half ago or 2 years ago, maybe, Finley had seen this paper mentioned, and he's like, oh, I would like to write LJ and LK. And he said, I'd love to read that paper. So I gave him the book, and he came back and said, it's a little bit heavy sledding. And it is. It's like it's a little bit hard to read, but the result was amazing. So NJ is a system of natural deduction for intuitionistic logic. And K is the natural deduction system for classical logic. LK is the sequent system for classical logic. And LJ is the sequent system for intuitionistic logic. Okay, now, these 4 different systems lay out rules, and they're either, well, so they lay out a system of proof rules that are complete for these, at least on the propositional case, for these, and even in the first order case for these systems. So what am I talking about? So let's just consider proposition logic. You would like for, consider propositional logic. You'd like soundness. And so if we write turnstile phi, where phi is some formula, to mean phi is provable, and oftentimes you might put on here something like, in NK, or some proof system, you might indicate which proof system you're using. To mean phi is provable in system, well, whatever. I don't know, maybe that's not clear. It's just so ugly to me. And I mean, I could get really, pedantic and write these out for every different system. So these are the 4 different notations to mean provable. And so when, you know, when we know the system when we know which proof system we're talking about, we can just use a turnstile. Okay. And that means to mean it's provable. Now, at least for classical logic, we have, you know, for classical logic, we have Boolean values provide models for classical logic. I don't know, you could call them T and F, or you can call them 0 and 1, or 1 and 0, I don't know, whatever you want. Any 2-valued set will do. And in fact, this goes back to Boole. Boole was working on Boolean algebra, and then it turns out there's a really, Halmos and others have done a really nice generalization of sort of Boolean algebras where you can even have more than 2 values. Okay, so what's the meaning of the connectives or the semantics? Well, let's see. This might be, you know, this is pretty redundant probably for many of you, but unfortunately, it may not be for everybody. That doesn't mean anything bad against you. So we got P and Q, if you don't already know this. We've got P or Q. Oh, come on. P implies Q. Oh, I should probably put not P in the front. And we could even write down P if and only if Q, but you know what? You don't need all of them. So let's say this is true, and this is true, and this is true, and this is false, and this is false, and this is true, and this is false and false. Okay, so you know how this goes out. So now if we look over here at not P, what do we get? We get false, false, true, true. Now, maybe I should write like bottom, because we're going to want a symbol in the logic, in the actual logical language. And so this is just always false. And what it usually is like, you know, I don't know how to begin to draw it. It's like well, I sort of do it. Like it's a vertical bar Gosh, if I could underline that vertical bar, that would be perfect. But it's a vertical bar with a horizontal line under it. So it's something like this. That's what bottom looks like as a character. So P and Q is true when? Only if P and Q are both true. So it's false in all the other cases. And P or Q is true when either one of them is true. And false if they're both false. And P implies Q is true if P and Q are both true. It's false if P is true and Q is false. And otherwise it's true. Okay. So now we can write this, and this is called the Tarskian semantics. I'll say Tarsky's semantics for propositional logic, classical. And basically you write, okay, sigma, and this is models. Now we can define this thing by recursion on the structure of phi. So we can say sigma models bottom. Well, it doesn't really matter what sigma is. And so what is sigma? I'm sorry. It's an assignment of truth values to variables. So sigma models bottom is just always false. Sigma models not P, if and only if, and this is really like an if and only if, it's always true. It's always false, I mean. If and only if sigma models P. So it's not the case that sigma models P. Sigma models, I mean, you can guess what the rest of this is going to be. Like it's P and Q, if and only if sigma models P and sigma models there is a LaTeX symbol called models Q. And so now classically, for or, we can just say or and this becomes an or. And finally, you can actually, you can kind of like get rid of the problem of defining this one by saying it's either not P or sigma models Q. And we could prove that that's equivalent. You could see if not P is true in either case, then it's true. And then, or Q, well, it's true if Q is true and it's false if Q is false. So this is equivalent to the this gives you back the equivalent of the truth table there. So any questions about this? Come on. I know this can't be completely clear. So a formula is valid if for every assignment sigma models phi. And in this case, we can write just models phi to mean phi is valid. Okay, this is a lot of stuff to take in just a, you know, I don't know, how long have we been going? 40 minutes. No one has a question yet?
I understand it pretty well. I think the only thing, I mean, that's kind of hard for me is, I guess, like the syntax of it. But other than that, it makes pretty much perfect sense. So it's just a new syntax.
So I should have. Oh, you all right? So which part of
Yeah.
the syntax? Oh, like the models and proves symbols. I mean, and
Yeah.
sigmas and stuff. But like and right, you know P and Q, and you know P or Q, and you know P implies Q, and
Right. So
not P. Right. So the formulas are not. It's just this other level of
right.
description. Okay. Thank
Yeah,
you.
because I think this is
Jessa.
like really similar to the type of stuff we did in like discrete, kind of. I guess
It
it's
is.
just, like, the truth
All
table.
this you should have learned in discrete. All right. So I don't know. Thank you, though, Jessa, for speaking up.
Oh, thanks. Yeah.
Can't someone else say something like, wait a minute, have I made a typo anywhere? Maybe. If I have, please call me out. All right. Does anyone know what soundness is? So I don't, if you know what soundness is, tell me. This is soundness of a proof system. Nobody knows? Come on, you won't, you like get everything that I have said up until now and nobody knows what soundness is. All right. All right. Soundness of a formula means that what we want is we want every formula that we can prove in our system must be true or valid. So every formula that we can prove actually satisfies every assignment makes the formula true. You know, we call these propositional formulas that have this probably have, are valid tautologies. They're true in every possible assignment. So soundness of a proof system says that if you can prove phi, then phi must be true in all the possible models. And completeness, what am I doing wrong? There we go. Completeness says what? Can you guess? Whoops. Come on. Keegan, what is completeness?
I don't know.
Okay, that's a good answer. It means that phi, if phi is true, then phi is provable. So what we really want for all if we have some kind of standard of what it means for a formula to be true, something like truth tables, we'd like to be able, our proof system really is most useful. The most useful proof system we could possibly have is one that completely captures every true formula is provable. Now, it could be that you have a, like you could have a really simple proof system that's complete but not sound. And you could just have, a simple rule that just says, here's a trivial it just says basically every formula is true. As an axiom. Like you could just have an axiom that says phi, where phi is a formula of propositional logic. Every formula, so every formula is true. Or is provable, I should say. But it's and this is what you worry about actually, is you worry about your proof rules could allow you to prove this. But if you prove that your proof system is sound, then you know that you're not in this bad situation. Like the kind of like, but I mean, I don't know. I can't write this big enough. I don't know. Maybe I'm going to sound insane for just a second, but when I discovered the following fact, I lost like a year of my life to an existential crisis. Girdle's theorem, how many people know? Does anyone know what Girdle's theorem says?
It says you couldn't have a proof system that's like complete, like, or Yeah. You
Yep.
couldn't. Yeah.
Right. There is no proof system for a language I should say, any language in which arithmetic is expressible. There is no proof system, and the caveat is you have to be able to express arithmetic facts or arithmetic equations in here. You have to be able to do arithmetic for any language in which arithmetic is expressible. That is both sound and complete. This is Girdle's incompleteness theorem. I don't know. I had just had this face that mathematics was where, you know, you could find kind of absolute certainty, but Girdle's incompleteness theorem basically says, yeah, except that there is no proof system that is both sound and complete once you have arithmetic. And the problem is that once you have arithmetic, you can do, you know, kind of like the rub is that once you have arithmetic, you can't spell. Once you have arithmetic, you can encode this is a formal language. So you can encode the formal language the proofs, you know, are about, and you can encode the proofs. You can make a data structure that looks like a proof using arithmetic. And then you can write a formula of the form this formula is not true. And you kind of derive a contradiction. Because if it's true, then the formula says it's not true. It's self-referentially saying, I'm not true. And if it's false, then it's true. So it's this crazy thing. And, you know, we could do a whole course on Girdle's theorem sometime. That would be actually pretty interesting to do. I took a course where we proved Girdle's incompleteness theorem as part of the course, but I don't know. Does anyone have any questions about that?
Is it true that in a non-self-referential system that this is not provable?
Not necessarily. Well, I don't know. You're saying, does every system which you don't have this power? I'm not sure. I'm not exactly sure. Maybe what that would mean. Every system that does not have like some kind of way of doing arithmetic in it. See, once you see, I don't know. Nobody probably knows. Like, I've actually thought that this could be interesting in machine learning. Because for machine learning, you have fixed size inputs. And so how could you make, like, you can't like input, you have like 5 inputs or you have 7 inputs. I don't know. I thought for a while, maybe you could use Girdle numbering to encode like lists or something. I'm not sure about that idea. I talked about to Chow about it, Chow Lan about it. But so, what does the Girdle numbering look like? Like if you have like you can assign numbers to each. You assign a number to each. I'm not sure I can remember this, but roughly speaking, you assign a number to each connective. Like, no, this is connective 1, this is connective 2, this is connective 3. And, you can use complete, like for, we don't need all the connectives that we have. We only need not an and or not an or bottom n implies. Those are enough to express any other connective. All right, so I'm not going to go down this line, but I mean look up Girdle numbering. And the basic idea is that it's just kind of insane. You basically encode, like if let's say if not is connective number 1 or number whatever 1, then how does it work? Let's say let's say it's number 3. Oh, what do you do? Then you take like 2 to the 3rd. I don't know. So you where do the prime numbers come? You sequentially would say, oh, and let's say that it occurs, so then I think like not P, and so if that's connective 3 and P is variable 7, then not P is something like, this is the first symbol, so it's the first prime number, and because it's connective number 3, it gets raised to the 3rd power times, now P is variable 7, but it's the second symbol, and the second prime number is 3, and it gets raised to the power 7, and so this is the number representing this not formula, not P. So it's something like that. Use primes and use the prime decomposition theorem to be able to get back to the original thing that the original formula. So you go back and forth. Okay. So we're getting far away from Curry Howard. So maybe what I want to do is I want to talk now briefly I hope I can do it briefly. It's a, you know, it's a whole philosophy. It's of mathematics. But when Tarsky discovered that, not Tarsky, when Russell discovered that, well, when Russell discovered Russell's paradox, which is consider the set of all sets that are not members of itself. And now, is that set a member of itself? And it turns out to be a contradiction, very much like Girdle's incompleteness theorem depends on this contradiction. So it's like, if it is a member of itself, then it's not a member of itself. And if it's not a member of itself, then it is a member of itself. So after Russell's paradox, mathematicians, especially, so it was like, what is it? It's like the set S such that S is not in S. The set of all S that are not in S. So anyway, you take Russell's paradox and it threw the mathematical world into chaos because everyone had been happily using Cantor's set theory for like 20 or 30 years. And were really making huge progress in mathematics. And all of a sudden, they couldn't trust set theory anymore. They might have been writing down paradoxical sets. And so this led Hilbert to who was the greatest mathematician at the time, to set off this idea of Hilbert's program. We're going to take mathematics. They didn't know about Girdle's incompleteness yet. We're going to take mathematics and put it on a firm foundation. We're going to develop a sound and complete proof system for mathematics. And it turns out you can't do it. Now, so Hilbert started on this program. So this was one way to try to fix this. And then they were able to fix this by changing set theory. So, you know, in Cantor's naive set theory, you could do this. You could do this. And then Zermelo and Frankel fixed it so that you couldn't. And then Hilbert was like, okay, and we want to develop a sound and complete proof system for all of mathematics. And then in principle, we can check every proof that we could do. And so, of course, Girdle's theorem crashed this idea, although there's evidence that Hilbert didn't believe it. That Girdle's theorem, he was getting old, like me. He couldn't understand the theorem. It was too much of a computer sciencey thing. It was all this meta level encoding of arithmetic that, okay, maybe he could see that work, but, you know, how did the whole argument go through? And then actually, for many years, mathematicians all thought, okay, who cares? This is some insane, weird, self-referential sentence. But then it turns out that there are real-life versions of real mathematical theorems that are independent of, that you can't, that are not provable, and like you fix your system. Let's say you take piano arithmetic. It turns out that there are formulas that are not provable in piano arithmetic with ordinary logic together with piano, the axioms for piano arithmetic. One of those, the first one that came out was Ramsey's theorem, which has to do with graphs. And he like made this property of graphs that essentially, and this is weird, this is another way of interpreting this thing that's come out, you know, like in the later. The size of these structures that Ramsey's theorem build grow faster than it's possible for any proof in piano arithmetic to grow. Like you can't build a proof that grows as fast as these things. Okay. It's fascinating theory. But Brouwer oh God, I can't remember his name. L.E.J. Brouwer. He proposed intuitionism as a solution. You know, in contrast to Hilbert's program. Hilbert's program failed. Intuitionism hasn't really failed. But, oh, come on. Quine, I don't know. Willard Van Orman Quine, who was a famous logician at Harvard, once said that like doing intuitionistic mathematics is like trying to do a prize fight with one hand tied behind your back. So what does that mean? What could possibly be tying your hand behind your back? Well, it turns out that kind of like the essence of it is that Brouwer says it's not the case that P or not P is true for every proposition. So P or not P is a tautology in classical logic. We could write the truth table. If you write the truth table, you'll see it's always true. Why? Well, because the only time P or Q is false is if Q is false, but not P is true in that case. So if you do an OR with this column and with this column, you see not P is always true. So P or not P is a theorem of classical logic. So this is a tautology in classical logic. And Brouwer said, look, I completely reject this idea because it can't be true for every proposition. Because for him, for Brouwer, to know the truth of a disjunction meant knowing which of the two disjuncts was true. So, like, you know, at this point, for example, you know, we could say like, consider the problem that we don't know the answer to of like NP. Is NP equal to P? That's unknown. But the claim is that NP equals question mark P. The question, that question this is always true. And what if for some reason we never learn whether P is equal to NP or not? Is it okay to use this? You know, it could be there have been attempts to prove that the P equals NP question is independent of set theory, of Zermelo-Fraenkel set theory. If that was true, it would be, you know, a huge thing. There are theorems that are independent, and what it means to be a theorem is independent, or I'm sorry, a formula is independent if you can consistently add it as an axiom or add its negation as an axiom. And there is like a very well-known one is the Continuum Hypothesis, which says that one version says that there are no sets between omega and a set of size omega or aleph sub 0, size aleph sub 0, set omega and the set 2 to the omega was that exponentially bigger. Is there anything in between there? And I guess the continuum hypothesis says yes, but you can negate it, which means there's none in that gap. And that is equally consistent with ordinary set theory, just as if you assume it. So there's no way to tell whether or not it's true or false in the proof system for set theory. All right, these are a lot of extremely big ideas. I was extremely attracted to this because I find the concept that every proposition is either true or false. Here's another kind of odd thing that you get classically. You get, for every P and Q, you get P implies Q or Q implies P. This is a classically true thing also. So I don't know. Think of another. What is another? Do we know the answer to Goldbach's conjecture yet? What about the twin primes conjecture? Take some other unknown mathematical problem like whether P is equal to NP and plug one of them in here and plug P not equal to NP in here. And so this is true. But the problems may have no bearing on one another. Like we always used to use Fermat's last theorem, and then Wiles came along and proved it. And so now we know it's true. And so we can't use that as a good unknown mathematical statement. Okay, so what's that? What are kind of the how much time do we have? All right, I could go till 7 p.m. tonight on this because we haven't written down, we haven't looked at the rules, at the proof rules for NJ, for the different proof systems. And I didn't tell you anything about, like here I told you what models for propositional classical logic look like. And even, you know, we can extend this and do models like that look sort of like this for, we can do hiding models for quantifiers so that you can include those. So where's my names of them? Okay, we got natural deduction for classical logic and sequence systems for classical logic. And you might think like, okay, like this means that there's proof systems that characterize these different things. Like intuitionistic logic can be characterized by a formal proof system. And it's kind of interesting to look at the difference. You can sort of see the difference in how the rules work for the classical. Oh, excuse me. I thought I could go to 7, but I think I'm going to fall asleep right now. Come on. Everyone is like dead. I feel like nobody likes me. I'm not kidding. It's so hard to talk to these faces. Nobody says anything. Nobody says, oh, that's interesting. I just told you the most startling fact discovered in the last century, Girdle's incompleteness theorem. Finn knew about it, and everyone else is like, is anyone there?
Yeah, we're here, but you know, it's like, what do we do with Girdle's incompleteness theorem? So our logic systems have a flaw.
No.
Okay.
They don't have a flaw.
They are inherently flawed, is the way you would look at it?
It's actually, well, okay. Finally, like one way that I came to see it is this, is that if you take the natural numbers, so consider and the natural numbers, or I'll say nat. Now this is countable. This is the smallest infinity. There are countably many formulas in any logic. But suppose the logic was suppose logic was intended to characterize the subsets of nat. So the set of all subsets This is not exactly right. This is not exactly right, but this is a way to sort of like think of, maybe a way to think about Girdle. What I'm saying is correct, but it's not necessarily directly related to Girdle's incompleteness, but it definitely related. The set of all subsets of NAT is an uncountable set. So that means there are subsets which cannot be expressed by any formula. So, you've got your formulas, whatever, F1, F2, dot, dot, dot. And the size of this set, even though it's infinite, is smaller than the power set of NAT, which I guess you could write, like S such that S is a subset of NAT. So that means there's some formula, if you think of these as kind of like the true things, there's some true things that countably many formulas can't capture. How does that sit with you?
Well, I guess it sits with me from the perspective of, yeah, I understand what it proves, but it doesn't have any utility value since I'm only interested in the set of things that's actually provable.
Well,
and when I get something that is unprovable, it's like, okay, I don't know if it's true or false, but it's still not in the set of things that are interesting.
Well, I mean, it certainly had a big impact on like Hilbert, who was the greatest mathematician of his time, trying to find this complete and sound proof system so that we could be completely solid on our mathematical footing. Well, maybe it's not that important. It was important to me. And I mean, it was important to Hilbert, but maybe then you go like, oh, okay, yeah, but that's all done. So now we know it. So what?
Well, yeah, but when I first found out about it, that's 30 odd years ago, I was like, wow, this is really important. But today I'm kind of like, okay, this is the case. There are bounds on what we can do.
Yes.
And
exactly.
I don't want to try to like go beyond the bounds, but there's lots of interesting things that are in the area that is useful and doable.
No, absolutely. I'm not saying that mathematics is no good or that it's inconsistent or that the formal theorems that we prove in a theorem prover are not true. No, they are.
They're in the set of useful.
Yeah.
They're in the set of provable.
Exactly.
And I know there's another set out there that is unprovable.
Yeah. And hopefully you don't run into one in the wild like people studying Ramsey theory did, or I don't know, there was the Paris-Harrington conjecture turned out to be like, unprovable. It's basically there are, so, you're right. And that's why most mathematicians originally, and maybe even to this day, kind of have a big, shoulder shrug. But, you know, once actual mathematically interesting problems started showing up that were outside the realm of, you know, systems which mathematicians thought like set theories enough to pretty much do anything. And then once things start showing up outside that, then it gets interesting. And there are a number of examples of real formulas that are like this.
Mm-hmm.
So, and intuitionism arose as a response to this. And intuitionism is the logic that corresponds to computation. So let me just continue. We're almost done, I think, right? Where are we at? We got 25 minutes. Did somebody else chime in there?
Oh, I was just wondering if you could like kind of give an example of what you mean by like the formulas that you're talking about.
Yeah, like
the logic formula. Yeah.
Oh, why are there well, even for like propositional logic, you know, we can say, oh, okay, what do we have as how do we describe it as a grammar? What are the propositional logic formulas? Well, let's say we have P, and what is P? P is some propositional variable. And maybe you want to say, okay, it's, you know, all strings of alphanumeric alphanumeric strings that start with a capital Latin letter. And then you have like not phi, where phi is a formula. And then you have phi 1 and I don't know, maybe I should, you know, I'm not sure if that's confusing. And that's one symbol. It's like, you know, I can write it like that. I don't know. Does that make more sense?
Yeah.
What if we use it doesn't matter. I mean, I can use the Haskell. Well, I'm going to use this here for phi 2. So those are all the formulas. Let me say here, just or.
Okay, yeah, that makes sense.
Okay, and
so would like operators count as a formula? Like
so if these are my formulas, though, where phi 1 and phi 2 are in previously constructed formulas, then there's an infinite number of formulas here. P-var is an infinite number, but there are no more than I can count them. Like I can assign them all natural numbers, even though it's just the same as like the natural numbers is an infinite set of things, but each individual number is, you know, follows at some finite point in the sequence. So it's kind of like the limit of that sequence is infinite. You can always get more. That's another big aspect, though, of Brouwer's intuitionism. He denies the existence of infinity and instead thinks of infinity as some kind of process that can continue forever. So I don't know if that sorted you out. Anyone else have any thoughts? Zach, what do you think about this? I don't really know you at all.
Yeah, I'm kind of new, so it makes sense. Up until the point you're getting into the propositional, right at the very end. No, sorry, not the propositional logic. That made sense. Just right at the very end, just this function. I'm kind of trying to wrap my head around it. But everything else I was following.
Mm-hmm. Oh, this?
Not that. Just what you just did for Jessa.
Oh, this doesn't make sense?
I'm trying to wrap my head around it.
Okay, well, I mean, this is called Bnf Specification, and it's a way of writing down a grammar that tells you what the things are that are in the set of propositions. And so, like, if you want to enumerate them, just look up Bnf and you'll see it. But, like, you know, like, let's say our propositional variables were like this. And I could go like P1, and now I could start to try to use P1 in all the ways. I could write not P1, I could write P1 and P1, and I could write P1, or this is actually, you know, P1. P1 implies P1. Now, rather than now going on to do something like, you know, I could do maybe here I should have done P1 comma and not P1. So you can try to figure out ways to enumerate all the formulas, then not P1 and P1 and not P1 comma and not P1 and keep going. And at each new connective, use all the things that you've previously used as subterms, and then add a new variable at some point along the way. Once you've done that, then you add, you know, and eventually you go on, and then all of a sudden you got P2 after you've done a lot of this. And then you do, you know, not P2 and not, and all that, and then you do all the combinations of P1 with P2, and then you just start growing and growing the set of all formulas. This set, there's an infinite number of formulas. So this is a grammar. And if you don't know Bnf, you might want to Google Bnf.
Got it. Thank you.
Yep. All right. So Finn, you've actually thought about some of this a little bit before.
Yeah.
Are you happy to that we're, I mean, I don't know. Do you have any thought? Anything to contribute?
What really made sense for the difference between intuitionism and like classical logic to me was like kind of thinking of it as like for a proof in intuitionistic logic, you have like a witness.
Yes.
You have like sort of a path that you can go down to verify it. Like it's sort of decidable, which like then makes a lot of sense for why the excluded middle is not doesn't make sense, because there's no witness. Like you can't so like for some formulas in intuitionistic logic, like Or if you have like concrete propositions, then you can prove the excluded middle, but you have to explicitly
Yes.
show which
Yes.
side.
That's good. Right. So this doesn't say that for every P or not P is true. This says that it's not true for every P. You can't generalize it. You can't prove that for all P, this is true. But what you can do is for some P, like for example, suppose P is that I don't know, I'm needing arguments, but I want to say that, you know, let's say it's the formula that says for all K, which is a natural number, even K or not even K. Well, we have an algorithm that can decide whether or not a number is even or not. No matter how big it is, we can decide whether a number is even or not. And so when he says a decidable, if P is decidable, then you can make an algorithm, and in fact, the decision procedure will say, you put in a K, so this is going to turn out to be a function that takes a K and then tells you, yes, it's even, or no, it's not even. And so that's the decision procedure for evenness that, you know, it's a trivial function. I mean, like equals 0 could have done something even easier, right? We could have said like, you know, is K equals like using Haskell notation, is equals 0 or not equals 0 K. Well, yeah, we could trivially tell whether an integer is equal to 0 or not. Now, but it gets very hairy when you go to the real numbers because it's undecidable if a real number is equal to 0 in intuitionistic logic. And that's because you may have suppose you represent, there's lots of different ways to represent real numbers, but suppose you represent a real number as an infinite sequence of decimal digits, and think of it as, you know, of digits 0 through 9 after the decimal point. So we're representing numbers between 0 and 1 as real numbers, and you can never tell if a number is 0 because you could look at it for, you know, you could write a program that looks at this infinitely long sequence for, you know, your entire lifetime, and it says, all I've seen so far are zeros. I'm still waiting for like a, you know, a 1 through 9 to show up, and then I know the number is not 0. But so you go for a century, you run this algorithm, and it says, all I've seen is zeros. Now, depending on what your application is, that might be enough to think it's 0, right? But in purely mathematical terms, it could be, okay, I give up, I turn off my algorithm, I'm not looking anymore, I'm sick of this. And the next digit could have turned out to be a 9. And then the number is not 0. So there are some, and this is what Quine meant by his comment. There are certain things that we take for granted in classical mathematics that, given two real numbers, you can describe whether or not whether they're equal to each other is also undecidable. You can tell if they're not equal. If they're not equal, you can eventually know it. You can semi-decide it. But you can't Now, so instead what they use is they use to reason about that an apartment relation. And you say, they're apart, these two numbers are apart by at least this much. And that gives you a stopping. You can look along, and if the decimal representations are exact out until you're at the position in the decimal expansion, which is smaller than how far apart you think they should be, then you know that they're equal. Or if they diverge from one another before they're so close that you can't tell anymore, then they are apart. And so it makes doing mathematics more difficult. But like you said, I think the fundamental thing you said, there's a witness for the truth. And so the other way to think of it is like that there's evidence for the truth. The truth of every formula or provable.
But isn't the generalization of what you said, that you can't prove that something is zero, is the exact same argument that you have in calculus, that the limit as n approaches infinity of a series of 0.9s is equal to 1? And you can't actually prove that.
Well, no. But 0.99, an infinite sequence of 0.9s is equal to 1.
Is equal to 1 in calculus, but it's not actually provable. It's provable because we have a way of manipulating the information before we actually measure whether or not it's equal to 1.
Well, it's kind of interesting. Calculus relies on, I mean, it turns out you can do calculus in constructive or intuitionistic mathematics. There is calculus that can be done. But it's always more like it would be, in fact, some physicists have looked at doing physics using intuitionistic mathematics because, well, you always get back this witness, and you're always, you kind of like don't care about this thing that doesn't actually exist of an infinitely long sequence. You can only ever, like, even no matter how fast you are, even if you could look at like an exponentially longer, like, I don't know what piece of the sequence every time, you still are bounded about how far you could look out. So if you want concrete evidence, it's good for engineering, right? Because in engineering, we only care about tolerances. Like, okay, these parts have to come together in some way, and they have to be within some distance of one another for the thing to work. If they're too close, you get too much friction. If they're too far, then you get all kinds of wear. But engineers always work with actual approximations to, like to what they want. They never assume that a part could be made exactly to a size. It has to be within some kind of range. And that's intuitionistic mathematics is really good for that kind of thing. So it almost makes more sense for engineering, but it also eliminates problems that these paradoxes that arise. I should say, there is evidence, and this is what, there's evidence or a witness for the truth of every provable formula. And it turns out that the witness is a functional program that has the type of the, when I convert We don't have enough time. Well, we have 5 minutes. So look, what is, how do I convert types or logic to types? So suppose that I have some, I don't know, and maybe I'm making it more complicated by writing phi, but by phi I mean like, some more complicated formula, and I can define by, I'll write like a little, I don't know, I'll write it in square brackets. And so this is the translation this thing is a thing that takes a proposition or a logical formula and translates it to a type. And so for variables, it's just a variable. For negation of some not phi, it's the translation of phi arrow bottom. That one's hard to explain, and so let's skip to the next one. The translation of phi 1 and phi 2 is equal to, so so this arrow here is the function arrow, is take the translation of phi 1, and in Haskell we'd write star. I'm sorry, in OCaml you'd write star. In Haskell we'd write the type is the Cartesian product. So this is the Cartesian product, phi times the translation of phi 2. I mean, I don't know. Should I use Haskell notation or what? The or becomes an either term. So I guess maybe if I just use this, so remember either in Haskell, and then implies just becomes a function type. So now you have an algorithm to translate, but let me just write down something. So if I have like, what was the type of SK? And here's the types. And so that's a type expression. So if I translate this one and I follow these rules, I'm going to get, oh, wait, this is not, this is the type. I need to, I'm sorry, I need this to be this. So that's a logical expression. And so what's the corresponding type expression is just write down the same thing. It's just change the double arrows into function arrows. Change the implies symbol into the arrow symbol, and the variables stay the same, and so we don't. So you know, like, what about something of type? And we'll do this more next time, and we really are kind of out of time. But I'm just right. Like, what if I wanted to find what's a function of type? You know, A. Maybe I should make these become lower because type variables in Haskell are lower. So, you know. So what if I want to translate like a formula that you know is true is that, like, if I know A and B, then I know A, so that implies A or B, or let's say or C. And so what's a function of this? So first of all, the translation of this into a type is that you've got a Cartesian, you know, you've got a product of A and B, and there a function from that to an either A, C. And here's a function that does it. Lambda xy arrow left x, because left is the injection that tells me, oh, it was the first disjunct. So this one has this type. And it turns out that for every type that you can write down, if there is a program of that type, then that type translated back into the formula is a true proposition. And so you can think of truth then as being that the type is inhabited. There's at least one thing having that type. If I did a write y here, and I said this is into either whatever CB, I could do that. That's a term that has that type. So there's this incredibly, well, it's the Curry-Howard isomorphism. Types, propositions are types.